superconducting circuits. In today class, basically we go to with the small recap of the previous session. As we know, Impulse Technology provides the simulation software for the material base, like first principle calculation software, which is based on density function theory, density function perturbation theory for the nanomaterial and for the nano devices. And we offer the simulation software for the quantum computing, like QTCAD software for the spin qubit devices and superconducting circuits. Apart from that, we also offer the simulation software for the solar cell, who working on the OLED, QLED, tandem, solar cell, organic LED. And apart from that, we also offer the equipment for the solar cells. In the last class, we also talk about like our partner, Fluxing, Nano Academic, and HZW. And you can see the product list also, like the SetForce software, Laos, NanoDecal, Rescue, QTCAD. SetForce Laos used for the solar cell, NanoDecal Rescue used for the material and device structure, like nanomaterial and nano device, which is based on density function theory and non-equilibrium gain function. And you can see the QTCAD we talked about earlier, like for the spin qubit and superconducting. And some other software you can see BDF MOMEC, which is used for the quantum chemistry, and DSPA, which is also DFT based software, which is based on plane wave. Now, let's talk about like the quantum technology. In earlier class, we discussed about like the domain of the quantum technology. You can see in the quantum computing, quantum cryptography, quantum sensing, and quantum random number generation. So the quantum computing, you can do the material science computation in a faster way, quantum chemistry drug discovery, and you can do for the portfolio optimization and logistic also. In the same way, you can do for the cryptography also, like for the communication, finance, and banking also. In the same way, you can do for the quantum sensing also, like for the mineral detection and GPS denied environment also. And you can do for the like random number generation also, like for the post quantum cybersecurity and online gambling also. In the last class, we talk about like the qubit implementation landscape. Like you can do in the multiple way. Like first one, you can see the superconducting circuits. Second one, spin qubits. Through the photonic, you can also do NB center, trapped ion, cold atom, and nuclear magnetic resonance. But in QTCAD, you can do like superconducting and the spin qubit. Like you can do find the property for the superconducting circuits like Maxwell eigenmodes, capacitance extraction, Joseph energy, and other parameters also through the QTCAD software. And in the spin qubit, you can find the property like for the qubit performance, charge stability diagram, Rabi oscillation, and other properties also. You can find the transport properties and device package properties also. Now let's talk about like QTCAD software. In the last class, we discussed about this is a multi-scale simulation software. It means you can do it at finite element also and atomistic level also. As you know, you can do for the like design the quantum device like QTCAD. Let's create a model of devices such as quantum dot, spin qubit, MOS structure, superconducting circuits, nanowire, and you can simulate like device physics also. Like you can find electric potential, electron density, wave function. You can do for the energy level, quantum confinement, and you can do also the Poisson equation and Schrödinger equation through the QTCAD software. You can predict the qubit performance also, like energy level, value splitting, tunnel coupling, exchange interaction, charge stability diagram, and the Rabi oscillation also. Apart from that, you can do for the superconducting circuits also. You can optimize the device design also, like gate geometry, material selection, oxide thickness, gate voltage, and the device dimension also. In the last class, we discussed about some unique feature of QTCAD software, which is cryogenic temperature. Like spin qubit devices and superconducting circuits work at cryogenic temperature. Like quantum device work at very low temperature, and normal tools fails here. But in QTCAD, you can do at a cryogenic temperature also. And you can see the solver also like Schrödinger solver to find the quantum state and the energy level also. And you can see the many body solver and master equation solver to generate a charge stability diagram and experimental actual measure also through the many body solver and master equation solver. Apart from that, you can see some other features also like value coupling to find value splitting affect qubit quality also. And apart from that, you can do the spin orbit coupling like for the motion with the spin and important for the control and decoherence also. You can do the magnetic effect, like you can include the Zeeman effect, and orbital magnetism also. Apart from that, you can do the Rabi oscillation, like for the qubit between states also. And you can find like micromagnetic EDSR also. You can predict Rabi frequency and leakage from the device geometry in the magnetic field gradient. You can do the tunnel coupling and exchange also. Like you can introduce tunnel coupling and exchange. You can do for the NEGF also, like to find the transport properties like IB curve and other parameters also. Apart from that, some additional feature also included, like point charge defect, lever arm matrix solver, parasitic volume and surface charge, and it also supports Jupyter notebook also. And it comes with the tight binding model for the value splitting. You can do the tight binding method also in the QTCAD software. Apart from that, in superconducting circuit, you can find like other parameters related to that, like capacitance matrix, Maxwell eigenmodes, Joseph energy, and other parameters also. Like here you can see the QTCAD atom package. Like at atomistic level, you can do the simulation also, and you can find like strain, settling, G tensor calculation, value physics, and spin orbit coupling also. Like you can do at atomistic resolution also. You can accurate the quantum device modeling with the tight binding method. You can predict eigenstate, value splitting, and spin qubit parameters also. You can do for the like quantum dot, value splitting, spin qubits, atomistic interface also, heterostructure, and charge transport also. Like in the earlier class, we discussed about the API structure of a QTCAD software. Like in the QTCAD, there are 5 packages basically, like device package and transport package and qubit package. Like in the device package, you can import some modules here, like mesh module, device module. Like in device module, you can create a data structure like material, potential, density, and wave function. And in the same way for the solver module, like for the Poisson linear, Schrödinger, strain solver, lever arm matrix solver, many body, quantum well, and in the same way for the post-processing module, auxiliary module also. And you can see the transport simulator also, like lead, junction, master equation solver, and EGF Poisson solver also. And in the qubit simulator, you can do for the EDSR, dynamics, noise also, and spectra. And you can save your output in a HDF5 format, BTU format, like to visualize in ParaView and other post-processing tool. And you can save the energy in the text format also. And you can plot through the Matplot and PyVista. And apart from that, 3 packages, there are other 2 packages you can see, builder package and atomistic package. In today's class, basically we go through the builder package also to create a geometry of a FDSOI to the OAS file and create a heterostructure layer. And after that, we can simulate through the Poisson solver and Schrödinger solver for the single quantum dot in FDSOI. And the same way, you can do the atomistic package. And we also create a simple example for finding the band gap for the silicon, like 2 or 3 line of code for finding the band gap, band structure basically of a silicon structure. In atomistic package, you can do the atomic structure and you can do the electronic structure finding through the tight binding method. And you can plot like band structure, density of state, projected density of state also. Now in today's class, we basically go through the tutorial of the Poisson and Schrödinger simulation of nanowire quantum dot also. Like the primary objective of this simulation to find the electrostatic properties and quantum confinement, like for the nanowire quantum dot using Poisson and Schrödinger solver. And like here we find the electrostatic analysis and quantum confinement, nanowire quantum dot modeling. Like here you can see, we basically use the 2 solver here, Poisson solver and Schrödinger solver. Basically, we're simulating a nanowire device where a quantum dot is formed using gate voltage, and we solve the Poisson to get electrostatic and Schrödinger to get a quantum energy level. Like when you apply the Poisson equation, it will create a trap for confine an electron or particles, and Schrödinger tells what happened inside the trap. Like here you can see we find this type of result also to this example nanowire. Let's talk about like nanowire and quantum dot. In nanowire is a one-dimensional structure, like in diameter range of 1 to 100 nanometer, and its high aspect ratio also, and it creates a quantum confinement region where we can trap electron or particles also. Like we talk about quantum dot region, where you can trap an electron or host to the potential well. And we do for the application like quantum computing, optoelectronics, LED, solar cell, bioimaging sensor, and advanced display technology also. And you can see the cross-section image for the nanowire. Like inner side, you can see the channel region, and you can the silicon dioxide and the gate. You can see the cut plane along the channel also. Like one end is the source and other end is the drain. Through the GMS GY, we create the geometry of nanowire. And we use two solver here, like Poisson solver and Schrödinger solver. To the Poisson solver, we create a trap. Like here you can see. First, we use for the doping concentration and applied voltage. We create a trap like potential well, and after through the Schrödinger solver, we find inside the trap like their energy level and their quantum states also. And in the simulation, a quantum dot is formed inside a nanowire by gate-induced electrostatic confinement, and its quantum state are obtained by the solving the Schrödinger state. It means through the Schrödinger equation, you can find the quantum state of the nanowire. And you can see the process here, whole process. Like first, we have to create a geometry file, like nanowire geometry file. After it, we have to create a mesh file. Once we create a mesh file, we have to create a Python file where you can define the QTCAD software and their packages also. Like first, we import a device package and their modules also, like a constant module, material module, device module, and some solver module like Poisson solver, Schrödinger solver. Here you can see. Once we import the module and define some parameters like gate source voltage, metal work function, we use the solver here, Poisson solver and Schrödinger solver. Once you compute the both solver, we get the result also. Like here you can see the proper. First, we have to create a mesh file. Like through the GMS, we can create a geometry file and we create a mesh. After we create the mesh, we create a device structure through the Python and QTCAD software, where we define the region and gate doping. Like here you can see material plus gate voltage. Once we create a gate voltage, we use the Poisson solver, like for the potential and band bending. It will create a potential well. And through the Schrödinger solver, we confine the electron states, which give the energy state of the electrons also, like different. And it will give the geometry property of quantum dot region also. You can see it will give the geometry property for the quantum dot. Here you can see the simple example here, like the one end is source and the other end is drain. And this is a channel region, you can see, and gate wrap around the channel. And once we apply the gate source voltage, it will create a potential well, which trap the electron here. And after we to the Schrödinger solver, we find the discrete energy level. Here you can see the discrete energy level. To the Schrödinger solver, we find the discrete energy level also and quantum dot confinement region also. Like here you can see, for any example, first we have to create a geometry file. Once we create a geometry file, we have to export in mesh file. Once you export in mesh file, you have to come to the QTCAD simulation where you have to write the Python code and import some packages here like device package and import some modules also. Once you import some module, we have to define the material and some parameters like gate source voltage, their device dimension. And after that, we use the solver to compute the parameters and get the result. Here you can see the workflow for the QTCAD software. First, you can see here, you can take the geo file to create a mesh file. This is the first one we create through the GMS for this nanowire. And apart from that, you can give the GDS file also with the Python file to create a mesh file. Once we create the mesh file, we define like the node and the physical group and the element also. After that, we assign the boundary condition like ohmic boundary, distillate boundary condition, different type of boundary condition. And we assign the region also, like the material, like source, drain, and drain oxide. We assign the material. Once we assign the material, we create a device structure, like define the device structure, like where we define the parameters source, channel, and drain region. Once we apply the solver, we get the result. Now let's move to the QTCAD software and create a nanowire structure. Everyone please open their QTCAD software and go on the hands-on training folder. Here you can see hands-on training folder. Open the command prompt by typing the CMD on top. Again, I see. And activate the environment first by typing command conda activate QTCAD. Once you enter, it will switch from the base environment to the QTCAD environment. Here you can see. Now you have to type here GMS to open the GMS software. I hope everyone open their GMS software. Please confirm. You can write in the chat box. Okay. Now click on the file option and there is option for the new. Click on the new and give the name here nanowire dot geo. Once you click on the save option, it's asking for the geometry kernel. Click on the built-in. I hope everyone had completed up to here. You can see the name also at the top section, nanowire.geo file. Now this is a GMS GUI. You can see some module given here like geometry module, mesh module, solver module, and post-processing module at the bottom section. It means GMS come with the 4 modules: geometry, mesh, solver, and post-processing. But for the QTCAD software, we only need geometry module and the mesh module.
I have a question. Can you hear me? So you have a two option. One is cascade, another one is the built-in. So what is the difference between these two?
Give me 1 minute.
Can you hear me now?
Sorry for my internet connection. Now you can see here 4 module here: geometry module, mesh module, solver, and the post-processing option. But for the QTCAD software, we only need geometry module and the mesh module. Click on the geometry option, and in the geometry option,
Can you hear me? Sorry to interrupt you.
yes sir.
So at the first time when you are just saving or uploading this nanowire.geo file, you have
Yeah,
a two option. Yesterday, if I remember correctly, you tell us to choose the cascade, but today is the built-in. Can you tell me what is the difference between these two options?
basically there are 2 kernel to use the software, but QTCAD recommend use the built-in kernel method. to create a geometry file.
Okay, so these two are the kernels mainly.
Yeah.
Okay, okay, fine. Thank you.
And in the geometry option, you can see the elementary and titles. Click on this and you can see the add option. Click on the add option. When you click on the add option, you can see the multiple parameters here, like point, line, B-spline, circle, circle arc. Click on the point option. And first, you have to assign the mesh length here, like 0.3, and go with the x0, y0 also, and z0 also. And click on the add for the point 1. I hope everyone had completed up to here. You can see the point also in the center for the origin 0, 0, 0, and 0.3. You have to click on add. After that, you have to assign the 1.5 here and click on add. I hope everyone had completed up to here. First, we have to go with the 0, 0, and 0.3 at the bottom section and click. Yes, sir.
Sorry to. So when I try to describe this mesh size at 0.3, it automatically my x and y automatically changes to minus something. So my geometry got changed. So will you please help me to retain the geometry for 0, 0, 0.
Basically, like here you can see, you can do the U from keyboard, you can type U. It basically undo the process. Let me show you again. Like
You are saying Q.
U from the keyboard U, undo option. Let me show you again. Here you can see when you click on the edit script, it will show the script option also. Remove the all section. Like here you can see in the nanowire.geo file. I don't have any point section now. Remove the point option. And now again,
Yes.
create from the starting point and directly give the value here 0, 0, 0, and you have to assign the 0.3 and click on add. Don't move your mouse on this screen, only type here. And again, give the value here 1.5 for the second point and click on add. I hope everyone had completed up to here.
Yes, now it worked.
Okay. Now, again, you have to give the value here 0. And for the y, you have to give 1.5 again. And click on add for the third point. Once you add the third point, again give the value here 0. And for the x, you have to give minus 1.5 and click on add. Once you add the minus 1.5, you have to give the value here 0. And for the y, you have to give minus 1.5 and click on add. Now you can see the 5 point at the 0, 0, 1.5, the second one, first point, second point, third point, fourth point, and the fifth point. I hope everyone completed up to here. Please confirm.
Can you show the script so that we can verify
Yeah.
to see if we are on the
Let
same
me show
page?
you.
Thank you.
Here you can see the script also. Point 1, point 2, point 3, point 4, and point 5.
1 second, sir, 1 second.
Basically, we create a circle like for the inner circle and outer circle also to create a proper nanowire.
So if we do control plus N on the script, so our structure will automatically be like this one.
What's it?
If we have, so if we have, we just copy paste your script and just type control plus N in our nanowire.geometry. So our
Yeah, it will. Yeah, it will create a structure.
Thank you.
Now again, click on the point option, like to create a outer circle also. Again, click on the point and here give 2.5, 0, and at the bottom section, we have to assign the 1.5 for the mesh length. And click on add. Once you click on the 2.5, you have to assign 0 here. And for the y, we have to type 2.5 again. And click on add. And again, you have to assign 0 here. And for the x, you have to assign minus 2.5. And click on add. After that, you have to give the 0. And for the y, minus 2.5. Once you do, at the top section, you can see the some parameters here, like press shift to hold the position or Q to abort. You have to type Q to abort. And now you can see the script also. For the 2.5, you can see 0.6, 0.7, 0.8, and 0.9. And we assign here 0.15 mesh length here. I hope everyone had completed up to here. Please confirm.
One more thing. If I add one extra point, then how I can remove that one from this notepad itself, removing? Or
Yeah, you can do this. Remove from here, like 0.9. If I remove this,
then how to reload that one?
and like Control S, and here you can see the reload script option.
Okay.
Reload script, and you can see it removed the 2.5 here. If I want to add again, 0 minus 2.5, 0, and add here, and Q2 abort. Now you can see here. Again, if I see the script, you can see the 0.9 here.
One more thing. There's
Yes,
a
sir.
0.1, 0.2, 0.3. It is going that if I remove 0.4, then I have to change all the numbering again.
Like if you want, if you remove the 0.4 here,
then I have to change the 0.5 to 4 and that.
no sir, no sir.
Okay.
Here, basically, you define the coordinate basically here. I hope everyone completed up to here. Please confirm.
Yes, my script is same, but my structure is not uploading. Actually, my script is same as it is also.
What is showing? Could you please confirm?
It is extended along Y actually, x-axis.
Okay. Change in the script here. You can see the script also. Like at the 0.1, we give the 0, 0, and 0.3. For the 0.2, we assign the 1.5, comma 0, comma 0, and 0.3. And the 0.3, you can see this is X, Y, and Z basically. X, Y, Z, X, Y, Z, X, Y, and Z. We only assign the X, Y value here, not Z. In the script, you can change and Control S, and you can reload the script. Let me give this command in the chat box also for up to now.
Yes, right now it works actually. Control plus Z and reload.
Once it completed, now we have to create a circle-like structure here. First circle, then second circle. For that, you have to click on the circle arc option here. click on this, and first you have to click on the first point. Here you can see 0.4, then the center one, and the 0.5. Again, in the same way, click on the 0.5, 0.1, and 0.2. Again, do for the same 0.2, 0.1, 0.3. Again, start from here, 0.3, then center, and the last one. It will create in a circle. I hope everyone completed up to here. Please confirm.
Yes, please go ahead.
Okay. Now do for the same for the outer circle also. Again, click on the circle arc. Click on the first one. Then again center. Then the ninth option. Again, click on here. 0.1, 0.6. Again, click on this here. Then center. Then the bottom section. Again, click here. 0.1 and 0.8. And press Q to abort. I hope everyone completed up to here. Please confirm. If you are facing any issue, please let me know.
Yes, I got
I have a question.
Yeah.
So, I mean, from the add option, I can see there's circle, and then we can specify the X, Y, Z for the center and then a radius. But why are we using points and using circle arc instead of using the circle itself?
There are multiple methods you can do. Like if you go to the inner radius, like you have to define the radius and prescribe mesh length. You can go with the circle also and the point also. To the point, we have to assign the circle arc also and the prescribed mesh length. Like for the same
So
way, like in the previous class, we also go to the box option, directly go to the box option. Here you can see the box to create a cube structure. In the same way, you can create the circle also. Like if you don't want to define the point option.
yeah, may I know, is there any advantage of using the points and defining?
No.
And
You can create through the circle also directly by defining the radius. Like
okay,
here you can see the inner radius is 1.5 and the outer radius is the 2.5.
yes, thank you.
Okay. Someone facing an issue, let me repeat this one. Okay. Let me remove the circle 1 also and circle 2. And reload the script. For creating the circle, what you have to do, click on the circle arc. Click on the 0.4 option first. Then the center one. Then the 0.5. Then 0.5 again. 0.1. And the 0.2. Again, select this one first. Then the center one. And the bottom section. And here you can do same way for the outer circle also. 0.8, 0.1, 0.9, 0.1, and 0.6. Point 1 and 0.8 and press Q to abort. Now you can see here. I hope everyone completed up to here. Now let's create a plane surface. You can see in the add option, there is a plane surface option. Click on this and click on the first one, this inner circle. Click on this. It will show the red color. Once you select the inner circle, you have to press E You can see press E to end the selection. Once you end the selection, it will show different line option here. And to select the second one, again select the circle 6 and Control Shift and select the second circle also. Control and select second one. And press E and then Q to create a plane surface. Once you click on the create the surface here, click on the mesh option and click on 2D mesh. Now you can see it created different region here. I hope everyone had completed up to here. Please confirm.
Could you please repeat this last part?
Okay, let's repeat. To create a plane surface, you can see the plane surface option here. Click on this and to select the inner circle, select this one and press E from the keyboard to end the selection here. Once you press E from the keyboard, you can see here arrow option given here. And again, you have to select the outer circle and Control and select the second circle and press E from the keyboard and Q to abort. Once you click on the 2D, you can see the mesh structure. If you not select the second circle, when you select the outer one, it will create a loop of basically the Boolean algebra here. Like black one also show like in the inner circle also. You can see the script also. Plane surface 1 and surface 2 1, 2. Basically, it will extrude the mesh 1 structure also. You can see the bottom section, plane surface 1 and plane surface 2 1, 2. I hope everyone completed up to here. Please confirm.
Okay, so completed up to there, but there is one question. If the
Yes, sir.
path of the circle, like X and Y, should be similar to yours one, or it could be different? Like
What?
4, 1, 3, 2.
What, sir?
The
Please repeat.
path of the X and Y paths for circle 1 to 3 up to 8 should be similar as you gave, or it could be anyone. Just
No.
I have perfect circles as yours one, but the path is quite different.
No issue, sir. You can go with this.
Okay, thank you.
Click on the 1D mesh. You can see the mesh defined. Now, once you create the 2D plane structure, what you have to do, you have to extrude basically. Create a nanowire region. We have to extrude. Like from the here, we extrude the surface and it will create a source region, then channel, then drain region. Let me minimize first. And now in the option here, you can see in the geometry option, at the bottom section, you can see extrude option. Click on this extrude. And the first one you can see translate option. Click on this. And you have to assign here 5. And you have to check this box, extrude mesh, and uncheck this one, recombine option. And you have to select all entities and titles here and click on the undo. You have to select the plane one here. You have to click on this one, this arrow. It will show color this like red color. And you have to press E from the keyboard. You can see it create a source region here. In the same way, select the plane 2 also. You can see it's so red color. and press E from the keyboard. I hope everyone completed up to here. Please confirm.
Yes.
Okay. And for the channel region, we have to create a channel region here. For that, we have to assign the dimension here 10 here. And mesh layer, you have to define 25. Once you assign the value here, you have to click on this plane 30, and you have to again type E from the keyboard. It will extrude the channel region here, you can see. Do for the outer section also. Select this plane and E from the keyboard. Now it create the channel region here. Again for the
For channel segment, for channel, can you please repeat?
what's this?
For this channel, check for the extension, can you please repeat?
Okay, let me
Last
see that. Now you can see the drain region. Like you can consider this one drain. After that, we have to create the channel region. Then extrude, translate, click on the translate option. And you have to give the dimension here 10. And you have to check this box, extrude mesh, and you have to uncheck this one. And assign the 25 value. And you have to select this plane. You can see this plane. When you select the plane 30, it will show the red color. And you have to type press E from the keyboard. And again for the outer section, you have to select this one, plane 72, and E from the keyboard.
Yes, right.
And now for the source region, again you have to assign the value here 5. And here also mesh layer 5. And again, click on this plane 94, extrude. And same for the outer section also, extrude. Now you type Q from the keyboard. Now you can see the nanowire, proper nanowire. And to remove this axis box, right click and uncheck this box. Now you can see the nanowire. I hope everyone completed up to here. Please confirm.
Yes, can you please share your script in the text box?
Okay, let me. Again, click on the mesh and you can see the 1D mesh. Then click on the 2D mesh. And after that, you have to click on the 3D mesh structure. Now you can see the 3D mesh structure for the nanowire. Now what we have to do, we have to assign the physical group here. Like you have to assign the drain band, gate band, source band, and the drain oxide volume, drain volume, source oxide volume, channel oxide volume. We have to assign the physical group now. For that, again click on the 1D structure. And go to the tool option. In the tool, you can see the option here. Click on this and click on the geometry option. Click on the volume label, and surface. And change from the description to physical name. Again, I repeat, go to the tool, option, click on the geometry, click on the surface label, volume label also, and change to the physical name. Once you click on this, you can see the volume here, volume 1, volume 2, volume 3 here. After that, here you can see the physical group option here. Below the physical group, you can see Boolean. At the bottom section, you can see the physical group. Click on this plus icon. Once you click on this option, you can see add and remove option. Click on add, and you have to click on the surface here. Like you have to create a drain band, this one gate band, and we have to create the source band. Click on the surface. Once you click on the surface, it's asking about the name here. We have to assign the name here. Drain band here. Drain and band here, you can see. Once we assign the name, you have to select this one, plane 1. Once you select, it will show the red color, and you have to type press E from the keyboard. It will select now you can see the name also, drain band, it given. Again, for the gate band, give the name here, gate band, and we have to select the outer circle, this one, this plane, this, and this outer section, not the inner one, outer one only. You can see it also the red color, outer one, and you have to press E from the keyboard. Now you can see it show the gate band option. In the same way, do for the source band also. Keep the name here, source band, and select the outer one, this one. You can see that, and press E from the keyboard and Q to abort. Now you can see the physical name here, source band. This one is the gate band, and this is the drain band. I hope everyone completed up to here. Please confirm. Okay. Now let's move to the creator. Give the name for the volume also, like so drain volume, drain oxide volume, channel oxide volume. Same for the source oxide and source volume also. For that, again, you have to click on the physical group, and now you have to click on the volume option. Click on the volume and remove the name here, and you have to assign drain, only drain, and click on this first volume and press E from the keyboard. Now you can see the volume given here, drain. Again, assign the value here, drain oxide. Again, select this one, volume 1 again, and press E from the keyboard. Now you can see the drain and drain oxide also both. Do for the channel also. First, channel. Select the first one, volume 3. Press E from the keyboard. And again, here you have to assign channel oxide. And again, select same volume 3 and press E from the keyboard. Do for the same for the source band also. Source. Select this one, volume 5, and press E from the keyboard. And again, you have to assign source oxide. And again, select this volume 5 and press E and Q to abort now. Once you open the geometry file, now you can see here drain band, gate band, source band, drain, drain oxide. Drain volume here you can see 1. Same physical group, you have to change here 2 for the drain oxide. And same for the channel, you can see the 3, but channel oxide you have to change to the 4 here. Same for the source 5, and for the source oxide you have to change to the 6. And Control S to save. And you have to reload the script here. Now click on the 2D mesh, then 3D mesh. And you can see the gate band, source band, and drain band. Let me share the script one.
I have a question.
Yes, sir.
I mean, so here I mean, after defining the surfaces and volumes, we go to the script, and we change the physical volume group from 5 to 6 and 3 to 4.
We can't. When we go through the QTCAD software, when we assign the same physical group to the 2 oxide, 2 volume, it will show the error. We have to change from this tag to other tag also. Like here you can see the script also. This one. Drain oxide also, and for the channel oxide also.
Yeah.
Like when you click on the 3D mesh, it will show the 3D mesh structure. And if you want to see the statistics related to that, click on this tool, and you have to click on the statistics. You can see the number of node here, point here, lines here, and same for the geometry. You can see 36 point, 56 curve used, 32 surface using in this geometry file, and the 6 volume defined here. You can see the 6 volume here, and the 9 physical group. Like 6 volume and 3 the surface, like gate band, source band, and drain band. Once you click on the 3D mesh, you can see the structure like this. You have to click on the file option, and you have to click on the save mesh. It will save the nanowire.mesh file in the hands-on training folder. You can see in the script also. File, click on save mesh, and you can see the path here, nanowire.mesh file on the hands-on training folder. Here you can see the nanowire.mesh file. I hope everyone completed up to here. Please confirm. Okay, now let's move further. And to create a QTCAD, like use a two solver, Poisson solver and Schrödinger solver. Open the VS Code. And let me open the folder here. File. And let's open the folder. In hands-on training, let's create nanowire dot and let's create a Jupyter notebook to visualize in better way for every single line of code. When you click on the create a Python file here, nanowire first IPYNG Jupyter notebook here, click on the code option, and it will first select the kernel option here first. For timing, let's write the code here. First, we have to import some packages here. Type here from QTCAD device package. We have to import constant like some elementary charge constant, Planck constant. We have to consider the CT. Sorry. You have to click on this detecting kernel option, and you can see the Python environment variable. Click on here. Wait. Now you can see the environment here now. It shows the restricted mode. That's why it's showing the error. Now you can see the QTCAD environment here. Click on here. Now at the top section, you can see the QTCAD environment. Now import some other library also. Again, from the QTCAD device package. Device, and we have to import a mesh library here. Mesh 3D. And we have to import mesh file to define the region and node point. Again, from QTCAD device package, we have to import IO module like for the input and output. Again, we have to import some other modules also from the QTCAD device package. We have to import analysis module like for the line cut along Z axis, Y axis to plot some ground state for satellite state. And to assign the material file, we have to import the material library here. Import analysis module, sorry, material analysis we imported earlier. As empty. Now we import some solver module here and device module to create a device structure for the nanowire. Again, from the QTCAD device package. Import device, and we have to import some solver here like Poisson solver and Schrödinger solver now. Now we have to import Poisson solver here.
I think from QTCAD.device import materials, you missed an S after material.
Yeah, let me check. Yes. And now we have to import some parameters also regarding the Schrödinger solver and Poisson solver also. And we import the Schrödinger and the Schrödinger solver here. Now we have to import some parameter related to the Poisson solver. For that, we have to import the library also, Poisson solver parameter library module basically. We have to import Poisson solver parameters. And in the same way, you have to do for the Schrödinger also. Now, at the last, we have to import the path live to define the path for the output directory and input directory for the mesh file. We have to import all these library to compute the Nanowire. You can run this also in 5. Now run again. Okay, let me import. And do for the Schrödinger also. And here also same for the Poisson solver parameters. Now run this. Now it computed successfully. Now create the next section of this code. And we have to assign like some parameter here, like gate source voltage, metal work function, and other parameters also. Like we have to assign the gate source voltage here, like 0.5. And we have to assign the metal work function, like for the conduction band age and the valence band also. And we have to use the empty here, like silicon here. And we have to assign the length here, basically device height in nanometer, because in the QTCAD software, all parameters and basic unit in SI unit, we have to convert into the nanometer. This is a device side, and we have to give the radius also, like 2.5 and in nanometer.
Sorry for interruption. So this
Yes,
is the
sir.
device height from source to drain, actually. This one.
What? What's that?
So this one is the device height from source to drain. That I have mentioned earlier too.
What's that? I didn't understand.
The height that you have mentioned, L total, this one is the total height of the device from source to drain.
Yes, sir. Source to drain, like channel length also, and the source drain or drain also. That's why it's 20 nanometer, 10 for the channel length, and 5 we consider for the source and channel, source and drain. Total 20 here. Now you can run this one also. Now let's create a next code. And we have to assign the path here basically for the nanowire. And we have to assign the path mesh. Like you can see, our mesh file is here. nanowire.mesh file. You can see. We have to give the name here. nanowire dot mesh file. Now we have to assign the some output directly, like to store the output, like HDF5 and other format also. You can create a output folder also, like to store all data in output folder. And we have to store in the BTU format also to open in the para view to visualize in better way, like for the hole density, conduction bandage, and other data also. And do for the energy also, like nanowire energy in text format. You can give the name here also, like nano wire energy dot text. You can do for the same for the line cut. We also go with the analysis tool to store the line cut along z axis, and same for the x axis also. That's why we have to store the in the text format also. And do for the x axis also. Now run this section of this code also. There is some error. Let me check first. Okay, no issue for the time being. Let's move forward. I'll check first. After that, we have to assign the change in the device structure to nanometer. Like here, you can see the mesh structure in the normal unit. We have to convert into the nanometer. For that, we have to give the scaling here. Like scaling, and after that we have to assign the mesh here. And we have to assign the path here for the path of the mesh file. And let me check first this one. Give me 1 minute. Let me check the other file also. Okay. Okay, now it's working. Now let's move forward, and we have to give the scaling here. Like scaling in nanometer. And after that, we have to assign the mesh here. Scaling, and we have to give here path here for the mesh. Now we can visualize also using the command mesh.show. Let's run up to here this code and check it's working or not.
Could you please update this code in the chat box?
Now, after that, we have to create a device structure. Like once we create the mesh and giving it the nanometer, we have to create a device structure here. Like you have to assign device and mesh. And after that, we have to assign the statistics here, like for the Fermi Dirac approximation and other parameters also. Like you can do the FD approximation here, and second one is the Boltzmann approximation, and second one is the FD approximation, normal FD, Fermi Dirac. And after that, we have to create a region here, like to assign the material now. For that, we have to assign for a device, we have to d.new region. And we have to assign for the channel. First, for the channel oxide. We have to assign the material here silicon dioxide. And same for the create for the source oxide. And we have to assign the material again silicon dioxide. And we have to create for the drain also same. And now we will have to move further for the channel source and drain volume. We assign the material here, like silicon for the channel region. and do for the like source also. We have to assign the doping here also. And doping is equal to 0. Same do for the drain also. And now we have to create a boundary condition, like for the drain band and source band and gate band here. For that, we have to assign ohmic band here. And same for the drain band also. And gate band for the we have to assign the gate source voltage also and the metal work function here.
Hi, I have a question.
Yes.
Um, is there any graphical user interface for us to define all these regions and then we generate the Python file, or we have to code it out every time?
For the time being, we have to go through the first. We have to create geometry in the GMS software, and after that, through the Python code, you have to assign the material.
So there's no GUI?
No, for the visualization, we have the GUI, but for the creation of Python file, we don't have GUI.
All right, thank you.
For up to now, let's run the code here, like for device, visualize the device here, d.so.
I think in scaling, instead of 1e minus 9, is it 1e9?
Let me check. Yeah. Let me run to 7. In your system is showing or not the structure in the visualization now? You can see in the QTCAD visualizer directly, like for the drain oxide channel, and you can see for the material also here. You can see for the material and for the region here also. Like if I uncheck this, you can see this one is a drain oxide, and same way for the source oxide also. You can check the drain band also, and the source band also. Once I close this, now you can see the other properties also here, like at a QTCAD visualizer for the potential here. You can do for the potential, charge density, electron density, hole density also, and valence band, conduction band also. And here you can see for the line cut also. Like you have to add the point first, and you have to compute. For timing, it's only show the 0. And in the same way, you can do for the iso surface also. Like here you can see, you can check the parameters and you can change the iso value. Now we have to assign the solver here, like Poisson solver. And we have to assign the tolerance level basically. And you have to assign the conversion threshold also. We have to decrease the tolerance level. It will take more time. We have to go to the -4, and we have to use the solver parameter now. And s dot solve to basically the self-consistent number of iteration it will show. Let's run this code. Close this. Now you can see the Poisson iteration also here, and the band here, boundary level. You can see the Poisson iteration and their time and their maximum error also. Now we have to create store the data also. We have to create array dictionary here. we have to do for the hole density also. Sorry. And same for the conduction bandage and valence band also. Now we have to store the data also. In HDF5 format, HDF5. And same for the now we have to save the in video format also, like to visualize in the para view. Now we have to line cut along Z axis, Y axis, like for the plotting the energy text format also. For that, we have to again create array. For the whole density also, for whole device, and potential also. And we have to assign the name also. And we have to do the analysis function, line cut. We assign the line cut name, and after it we have to assign the mesh array, and we have to assign the value here also, from which axis to which axis we have to do. Like 0, 0. And we have to assign the array name here. And you have to do the same for the z-axis also. Let me do the same. Save line cut. And we have to plot the potential along z-axis also. Line cut. For the mesh. And we have to assign the range also. And we have to assign the title here. Now we have to plot the band diagram also. For that, we have to assign the coordinate here also for a device, and we have to assign the for up to now. Let's run the program here and see the band diagram first. In 949, there is some error. Let me check. Conduction bandage, and we have to change the function here. And let's run this again. Okay, now it's issue on the line 55. Now let's move further and create a Schrödinger solver. Once we solve the Poisson solver, we have to assign the confinement potential, which is stored in the through the Schrödinger solver, and find the number of energy states. You can choose the any carrier like electron to host. You can choose. And we have to assign the Schrödinger solver parameters also. Nice. Now their tolerance level also. And we have to assign the number of state also here. And we use Schrödinger solver. And we have to print energy here. And you can plot the ground state and first excited state, second excited state also. Let me run the previous example which I did. This is the same one. Like in the visualizer, you can see the your device structure, and where you can see the region and material and other parameters also to compute. And this is a reset camera option. You can reset also at a particular coordinate. Like here, you can see the number of Poisson iteration, and you can see the where all data is stored, like in output folder HDF5 format. Same for the energy also. Electric potential, band diagram, and the hole density. Potential you can see here, and the ground state, first excited state, and second excited state. And if you see the output folder here, it will create an output folder where you can see the VTU format. You see in the channel section. You can see nanowire energy.txt format and nanowire HDF5 format, VTU, and line cut along x-axis and z-axis also. You can see the line cut along z-axis and x-axis also. And in the terminal, you can see the geometry property of a quantum dot also. Here you can see. And the energy level after solving this Schrödinger equation. And apart from that, like for the spin qubits, let me show you the example first. Like in the previous example, previous session, we go through the cube option. I already share this Python file. Like solving the Poisson equation in charge-free box, where you introduce the Poisson equation only. And if you want to create a geometry through the QTCAD builder, you can use this Python code also. And you can see the theory part also included in this Jupyter notebook, like for the electrostatic potential and electric field also. You can see there's some theory part and boundary condition you can see here, like ohmic boundary, gate bands, Schottky, and other display boundary condition you can introduce. And in the same way, we apply the 1 voltage and 0 volt. And we create the geometry through the QTCAD builder option in this example. Like this one. We use the QTCAD builder option, and you can see the theory part also, like their reference and their function and default value. You can click on this link directly to see the parameter related to that. Now you can see it created the box structure. And after that, we assign the some physical group here, box bottom, box top. Same way like for the nanowire also. After that, once we create the mesh file, we have to move to the QTCAD, like simulation with QTCAD. And you can see we import the mesh library, device, and simulation also. And you can see we import some important library like for the device, material, and constant also. And here you can see we use the Poisson linear here. And QTCAD support nonlinear Poisson equation and Poisson equation both. And you can see we scaling into the nanometer. After that, you can see the mesh structure also. If you use the Jupyter notebook, you can directly see here, not open the Google Chrome. It will directly show in the VS Code directly. Like here you can see the region box and bottom also. And after that, we give the carrier is equal to electron. You can change to the holes also. If we don't assign the electron here, it will automatically select the default value, which is electron. And here you can also see we set the temperature here also, like 1 Kelvin. You can change to the millikelvin also. And if you go with the default parameter, it will give the 1 Kelvin here. Here you can see we assign the material is equal to vacuum option. Now we assign the boundary condition and device dot show. Now it creates a device structure and it will open here, you can see. After that, we use the solver, Poisson solver. And compute here, boundary level. And now plot the line cut. Here you can see the orthogonal electric potential. You can export in the BTO format also by defining the script directory. Here you can see the electric potential also. And you can see in the 2D surface also in the same way. And you can see the conclusion and the future step you can do in this example also. Apart from that, if someone facing an issue, please let me know. Anyone have doubt regarding the nanowire quantum dot or cube box dot Python file?
Can you explain the Nanowire Python file that we wrote so that like a gist and revising?
Okay,
Because I lost track after the array dict and analysis line cut for the nanowire that we did.
Basically, first we have to import some library from the device package, and we import some library constant, analysis, and material also, and device module to create a device object. And after that, we use the solver, Poisson solver, Schrödinger solver, and their parameters also. Like Poisson solver to find the electrostatic potential, and to like create a potential region, potential well to confine an electron. After that, for the Schrödinger solver, we find the number of states also, eigenstates in the quantum dot region, and we also find a geometric property for the quantum dot. Here you can see we assign the gate source voltage, metal work function, and device height in nanometer. Same way radius also. And after that, we assign the path here, script path, like for the nanowire.mesh file and for the output folder also, like where you have to store these all data. After that, we load the mesh file and plot the mesh.show function to visualize directly in the Chrome section. If you write simple Python code, if you write a Jupyter notebook, it will show in the direct VS Code. And you can see after that, we create a device structure, like to assign the Fermi direct statistic here. And we assign the material for the channel oxide, like silicon dioxide, outer circle, cylinder. Same for the source oxide and drain oxide. And for the channel, we assign the material silicon and doping also. After that, we create the boundary effect like source band, drain band, and in the gate band, we assign the gate source voltage to create a electrostatic potential which trap electron basically. And after that, we visualize the device structure with the command d.show, and we set the camera position also to change the like coordinate basically. And after that, we introduce the non-linear Poisson solver here. You can see, and after that we use the self-consistent solution like to number of iteration for the Poisson equation, and we save the line cut also like in the for the conduction band, valence band, hole density, electron density, and you can see the line cut also here along z-axis and x-axis also. After that, we plot the potential here, and after that we plot the band diagram. Once we plot the band diagram, once we create the potential region, after it we create the Schrödinger solver. We introduce the Schrödinger solver. We introduce the conference carrier, basically electron, like to trap any particle, electron or holes. Here we consider the electron. You can change to the holes also. And after that, we introduce the solver here, Schrödinger solver, and give the threshold level, like tolerance level, and the number of state to consider. After it will solve the Schrödinger equation and print energy level, like the number of energy level quantized. And after it plot the geometry property, like for the quantum dot region. And if you want to plot the like orthogonal way, it will plot in the orthogonal way for the hole density and potential also. And same for the ground state, first excited state, and second excited state also. Once you run all this, it will show the data related to that. And you can see in the output folder also. Here, nanowire.hdf5 and BT5. You can open in ParaView also, like to visualize in better way and plot a 2D plane also. And apart from that, you can explore the other example also, like in QTCAD software given. Like if you click on this example option, you can see the practical application here. Click on this, and you can see the FDSOI, gallium arsenide, and germanium hole. You can see if I click on this and click on this one, if I run this one, fully depleted silicon on insulator, it will create like this structure, like where you assign the drain and some gate here, like plunger gate, to create a quantum dot region. Here in this example, you can see we use the QTCAD builder option to create a structure for the FDSOI. Once you create a mesh structure, the second Python file you can see, you use the linear Poisson solver. And third one, you can see that for the Coulomb blockade, you can use the Coulomb peaks. Charge detection you can do, find the chemical potential also, and double dot fully depleted silicon insulator also. And apart from that, like in the hands-on training, you can create a Python file also, like for the finding the band gap. Let me open this one. Here you can see, like if you want to visualize a simple band structure, you have to write this code for the band structure for the silicon here. You can see we assign the first we import the numpy and you import the QTCAD atom package. to visualize the silicon band structure. Once I run this, and in code you can see we assign the lattice constant and unit cell zinc blend structure. And after that, we compute the band structure like this. You can do for any material file like silicon and germanium, any alloy also, and like the gallium arsenide, any material you can visualize in the to the atomistic package also. And for API reference, you can move to the documentation for the API reference, like for the atomic package, device package, transport package, and qubit package. For up to now, if anyone have doubt, please ask. And we also share some resources regarding the fully duplicate silicon insulator and other Python file also. Anyone who have doubt, please ask. You can write your query in the chat box also. And apart from that, you can follow the YouTube channel also. There are multiple videos related to the QTCAD software, like for the Nanowire and for the other devices also, like how to create a geometry file and other things. Anyone who have doubt, please ask. Okay, and please join the Friday session also, like where we have to introduce the like quantum compute superconducting circuits also, like where we find Maxwell eigenmodes, capacitance matrix also. And we also continue with the fully depleted silicon insulator, where we find a single quantum dot region and double quantum dot region also. And we also go through the EDSR qubit performance matrix also, like find the Rabi oscillation and other property. Yes, sir, you can do the for the quantum computer device design. Like if you want to find property related to that, like for the Coulomb blockade, for the qubit performance matrix, like if you want to find the noise and EDSR, Rabi oscillation, and other parameters, you can go through the QTCAD software to find all these parameters. Like first thing, you have to create a qubit also. Through the qubit, you can do the spin qubit device. And for the spin qubit, you have to create first quantum dot region. And for the quantum dot, you have to use the Schrödinger solver and Poisson solver also.
So I have one query actually.
Yes, sir.
So if I have relaxed my this one structure somewhere else, or if I have some structure, so can I import this to this
What's that?
QTCAD?
Like
I
material one.
Yes. Like silicon. If I have a structure of silicon germanium somewhere else, I relaxed, so I import this
Yes,
one
sir.
to
You
there.
can import in XYZ format.
Good. And can I export the magnetic structure through here? Like suppose I have the structure of this FEPS3 oblique MOS2. Can I export this one through here?
Yes, sir. For the reference, yes, sir. For the reference, you can see the documentation also. Let me show you related to the atomistic package. When you click here, atom package. Multi-stage simulation. Like this is for the silicon here, germanium, and with the rough interface between silicon germanium and spacer between silicon germanium well. For finding the property, you can do the atomistic package, sir. And Like you can visualize in the Vesta also.
Thank you.
And apart from that, if you want like proper DFT base, we have different software for the DFT.
So right now I'm using VASP. That's why I'm asking.
Okay. For the VASP, we have a competitor for the VASP, like DSPA, which is also based on the plane wave, and where you can find like all parameter related to the molecular dynamics and EV method and elastic constant, dielectric constant, frequency, multiple parameter you can find. Like if you're interested, you can directly contact us. We can give the trial version of also the DSPA software.
Okay, thank you for the information.
Anyone else who have doubt, please ask. Okay, please join the Friday session also, where we have to learn about the fully duplicate silicon insulator also and superconducting circuits. Thank you everyone for joining the today's session.